So here they're talking about, again, that empirical rule. That empirical rule, remember, just says that there are these three magic numbers, that 0.68 is some probability, 0.95 is another probability, 0.997 is another. That was the probability that X falls within one standard deviation. I know this notation probably doesn't make sense. Was that represented by 0.68. X falls within two standard deviations. That's all they mean by the empirical rule. And then X falls within three standard deviations. Okay, just so we remember. Okay, we will now consider probability questions that cannot be answered using the empirical rule, because we kind of feel like we kind of get the empirical rule now, especially when you have a graph in front of you. It makes it a lot easier. Let's revisit that foot length example we saw before. Let's go back to our example of male foot length and ask a question that cannot be answered using the empirical rule. We're going to figure out, okay, how do we do that? What is the probability that a man's foot length is more than 13 inches? Okay, so I remember that the mu or the mean was 11. That was like your average foot length. And then the standard deviation was 1.5. So the question they're asking about is 13 inches. 13 is not really one standard deviation more than 11 or two standard deviations more than 11. Yeah, if it was 14, now that would be nice. I think they asked that on the previous page, because that's exactly two standard deviations above. So that's something I can use the empirical rule for, because this 13 they're asking about isn't an exact, a whole number value of standard deviations above or below the mean. It's going to be a little tricky. So because 13 inches is not, yeah, exactly 1, 2, or 3 standard deviations away from the mean, we can only give a very rough estimate of the probability at this point. To find the probability, we will determine the number of standard deviations 13 is above the mean, and then use technology to determine probability. We would never try to calculate this by hand. It would be silly, I guess. We use technology. We'll start by practicing how to find the number of standard deviations an X value is above and below the mean. So this one, because it's not a whole number of values above or below the mean, like we kind of just talked about, it's going to be some decimal or fraction, but it's still, and then we'll figure out how to use it or to find the probability that way. Okay, we will start by practicing how to find the number of standard deviations an X value is from the mean. Okay, how many standard deviations above the mean is a male foot length of 13 inches? 13 inches is 2 inches above the mean. How many standard deviations is this? So since a standard deviation is 1.5 inches, 2 is 2 divided by 1.5. It's about 1.33 inches, or inches, 1.33 standard deviations above the mean. So we'll combine these two steps into one equation. You take 13 inches, which is the value they're interested in, minus 11, which is mu, 13 minus 11, and then the denominator is going to be sigma. So it looks like mu, or no, sorry, the X value you're interested in minus the mean over sigma. That's how you find how many standard deviations you are above or below the mean. And they have that here. In the language of statistics, we found the z-scores for a male foot length. We don't know what that is yet necessarily, but now we're getting into it. 13 inches to be z equals positive plus 1.33. So that we just figured out 13 is not one standard deviation above the mean. It's more than that, but it's not two standard deviations above the mean. It's less than that. Somewhere in between 1 and 2, we figured out it's 1.33 using this formula here. Or to put it another way, we have standardized the value of 13 into standard deviation units. A foot length of 13 inches is 1.33 standard deviations above the mean. In general, the standardized value z tells how many standard deviations below or above the mean the original value is. The formula for the z-score is, so we call that a z-score. How many standard deviations above or below the mean you are. Z-score, yeah. Equals the number, remember this used to mean number back in the day, number of standard deviations above or below the mean X is. So they should give you an X value, just whatever value. You can figure it out using this formula. Okay, using our familiar notation, we can rewrite the formula as, we use the X up here because that's what we've been using for our variable, but they use specifically little x, but you know what I mean. For values X above the mean, mu, the z-score will be positive. For values of X below the mean, the z-score will be negative. I guess because it's positive if you're above the mean, you're adding to get above the mean, but it's going to be negative because you're subtracting to get below the mean, is the idea. Okay. Let's scroll down and see what else we can figure out here. let's look at some examples just to kind of reiterate this idea. Let's calculate another z-score. Let's practice finding another standardized value. So it's going to be some value we're interested in that's not 1, 2, or 3 standard deviations above or below the mean. It's some kind of decimal value of standard deviations. What is the standardized value for a male foot length of 8.5 inches? What does this number tell us? Well, we know that the z-score, or the number of standard deviations above or below the mean, is the value they give us, x minus mu divided by sigma. Okay, so they gave us 8.5. Subtract the mean. I think, we're still talking about male foot length. In the same example, we remember that the mean was 11, and then the standard deviation was 1.5. So if you calculate that, subtract 8.5 minus 11, that would be negative 2.5. Negative 2.5 divided by 1.5 is negative 1.67. And I put the squiggly equal sign because that means it's approximately equal to, I had to round to get this point. I think it's negative 1.66666, but I rounded it. A z-score allows us to compare x values from different normal probability distributions. Here are several examples. For one example, female foot length revisited. Women's foot lengths also have a normal probability distribution, but the mean is 9.5. Okay, I got to remember that. Mu, I'm sure I'll be using that to do something, 9.5. And the standard deviation, this new one, still talking about foot length, but now it's for females, so it's a little different, is 1.2, not 1.5 like male. Sam's foot length is 13.25 inches, okay. And Candace's foot length is 11.6 inches. Which of the two has a longer foot relative to his or her gender group? So I guess we're assuming Sam's a male and Candace is a female. I guess that's what they're trying to say. They probably should have specified. I think. So I guess we're comparing Sam. Okay, Sam, maybe I should color code it. Shoot. Blue. This is like bad for gender roles and all that, right? Sam is a male. I'm a man. I like blue. Like people always think babies that her boys like blue and girls like pink. I don't know. But anyway, so Sam, I'm assuming he's a male, 13.25 inch long foot, and Candace, that's definitely a female name, I think, 11.6 inch foot. Okay, maybe I'll do hers with purple. Which of the two has a longer foot relative to his or her gender? So I guess which one is more standard deviations away from their mean than the other? So how close is Sam's foot length to the mean for males, and how close is Candace's foot length to the mean for females? What we can do is just calculate their z-scores and compare them. Which one has a larger z-score, I guess, is what we're going to do. Yeah, has larger z-score. Okay. To make the comparison, we standardize the values giving z-scores. So Sam, this is kind of hard to see. Maybe I can kind of zoom in here. Here we go. These values are super tiny. So for Sam, we're remembering that I think we're comparing his foot length to other males. That's why it says the mu, the formula was x minus mu over sigma. So the mu is 11 and the sigma is 1.5. But in Candace's case, when we're calculating the z-score, her mu is 9.5 because that's the mean for females, and the standard deviation for females is 1.2. So we're calculating z-scores, but the mu's are different and the sigmas are different because we're comparing different values with different sigmas, different mu's. So it looks like if you do the calculation with Sam's foot size, you get 1.5. So his foot length is 1.5 standard deviations above the mean. And I know it's above because I get a positive z-score and because his foot length is greater than the average. And then Candace, when you calculate hers, she has 1.75. Her foot length is 1.75 standard deviations above the mean because her z-score is larger than his. Her foot length, Candace's foot length is longer relative to other women. That's how we would compare, because I'm not really comparing Sam's foot length to Candace's foot length. I'm just comparing Candace's foot length to most of the other female foot lengths and Sam's foot length to most of the other male foot lengths, if that makes any sense, hopefully. So the example, let's talk about test scores now. The test scores in Maria's class have a normal probability distribution with a mean of 70 and a standard deviation of 5. The test scores, I need to scroll over here. In Lamar's, let me get that, sorry. Lamar's class have a normal probability distribution with a mean of 85 and a standard deviation of 10. So Maria and Lamar, they're in two different classes. The average test score in her class was 70. The average score in Lamar's test class was test class. Lamar's class for the test was 85. But for Maria's class, the standard deviation was 5. So most people were within 5 units away from 70. So a lot of people got between 65% and 75%. But in Lamar's class, the standard deviation is 10. So most people were kind of in a wider area. I add 10 and subtract 10 from 85, which is mu. 85 plus 10, 95, 85 minus 10, 75. So Maria scored a 76 and Lamar scored an 80. Why? I think they mean who did better on the test relative to their classmates. So then we'd have to calculate the z-scores because we're not, again, this is like the foot size with the male and the female. I'm not comparing Maria's score to Lamar's score because, she was maybe in a harder class. Maybe the instructor wasn't as good a teacher. That's why the test scores were low. Lamar maybe in a better class with a better teacher or something or whatever. I don't know. We're not going to compare her to him. We're going to compare her to her classmates and compare him to his classmates. So if I take her score and I subtract the average value for her class, which was 70, and I divide by the standard deviation, which was 5, I get this calculation here. 76, her score minus the mean 70 is 6 divided by 5, the standard deviation, I get 1.20. So Maria scored 1.2 standard deviations above the mean for her class. Okay, now we'll compare that. Now just set that information aside and think about Lamar. So his score was, I'm still using the same formula. His score was 80 minus the mean, mu, 85 in that class, divided by sigma. The standard deviation there was 10. 80 minus 85 is a negative number. Negative 5 divided by the standard deviation 10 would be negative 0.5. Lamar scored 0.5 standard deviations below the mean for his class. Relative to the respective classes, Maria performed better on the test, even though her score was lower than Lamar's. Because again, she did better than the average person in her class, and he did slightly worse than the average person in his class. But hey, they both passed the test. So I hope they don't argue about it and say, I did better, like a child would do. Anyway.